Hello, I'm Yaqing. I will introduce our robophysical study of force sensing for least resistance traversal of cluttered large obstacles. This work was presented at APS March meeting 2024. Many applications requires the robot to maneuver in complex environment with many large cluttered obstacles. Now the dominant approach for a robot moving in a complex environment is to first visually scan the environment and create a geometric map. Then the robot applies an artificial potential field to the map and plan a path to avoid obstacles. However, when it has to physically interact with the obstacles, even the most advanced legged robot fail to do so, because unlike artificial potential field framework serve as the foundation for most robotic navigation, the robot lack a conceptual framework to model the physical interaction with the obstacles. To remedy this, our lab tried to establish a potential energy landscape modeling to fill as a framework. Rising from the very fundamental concept of potential energy landscape modeling well captured the robot obstacle physical interaction over a variety of scenarios, inspiring new robot design, actuation, and reactive control. Here I will focus on the model system where the robot will traverse these beam obstacles. Our robotic study were inspired by the animals. We observed that when traversing a pair of grass-like beam obstacles, the cockroaches usually transition from what we call the pitch mode to a roll mode. Here is the pitch mode. The animal pushed down the beams and traversed, where its body pitched up a bit due to the resistance from the beam. And here is the roll mode. The animal rolled its body and goes through the gap. To understand how these mode transitions emerge from physical interaction with the beams, and how a robot can do so, we first came up with this simplest model and only considered the potential energy of the system, which varied with a body position and orientation when it's in the neighboring area of the beams. Here is what it looks like when the body is in the middle of the beams, as a function of body pitch and body roll. We can see that there are three local minimum basins. In the middle is a pitch basin, which corresponds to the body pitches up. On the two sides are the roll basins, which correspond to the body rolled into the gap. The local motor transition from pitch to roll mode on the landscape is the body escaping from the traction of pitch basin and reaching the roll basin, where the body will overcome a transition barrier. The body will transition with the least effort via this saddle point, similar to traversing a geological barrier. In previous studies, inspired by the animals, we hypothesized that the kinetic energy fluctuation from body oscillation could induce this destabilizing barrier crossing transition even without sensory feedback. To test that, we created this feed-forward robotic physical model propelled forward without any sensory feedback, and we applied vertical oscillation to provide kinetic energy. Here are two representative trials. On the top, the robot stayed at the pitch mode because without oscillation it was trapped in the pitch basin. Below, the robot quickly transitioned to the roll mode because with sufficient oscillation, the robot got enough energy to overcome the transition barrier to escape from the pitch basin to the roll basin. This example shows that the potential energy landscape modeling is a good framework for capturing and predicting the locomotor mode and transitions resulting from physical interaction. A natural question is, how can we apply this framework to the uncharted environment? As the potential energy landscape modeling is risen from the physical interaction with the obstacles, we hypothesize that the force sensing will give the landscape to uncharted environment. In detail, from mechanics, we know that the gradient of the potential energy is the external normal forces and resulting torques, after considering the gravity effect. When the robot physically interacts with the terrain, it can sense the contact force and contact position. From the contact force, the robot can estimate the normal force. The cross of the force arm and the force will give torque, which can be used to calculate the landscape gradient. So this tells us that the robot can sense contact force and torque and position to get the gradient and further reconstruct the landscape. Here we elaborate on our method using a robophysical model. We build a robotic system similar to that from the previous study. Here the robot's roll and pitch angles are not free but fully controlled. To sense the contact force with each beam, we separated the robot into two parts and connect each part with the robot mainframe via a 3D force sensor. To sense the contact position with the beams, the robot surface is covered with sectioned contact sensors. To check whether the force and torque sensing can enable landscape reconstruction, we took the first step to let the robot systematically sweep the rotational state space. We varied the robot roll angle from 0 to 40 degrees and pitch angle from 10 to 40 degrees, which resulted in over 300 trials. In each trial, the robot was fixed to a certain rotation and propelled forward at a constant speed. Here, the robot was sensing the contact force in the fore-aft, lateral, and vertical directions, and contact positions with the beams on the left and the right side of the robot surface, and calculating the resulting torque in real time. Here, these color-coded solid curves are the measured force in fore-aft, lateral, and vertical directions, and torques in the roll, pitch, and yaw directions from a representative trial. From them, we can calculate the normal forces and torques as the dot curves. Let's only keep these normal ones as they are the conservative part. When compared to the landscape gradient at the dashed curves, we can see that they matched well, which shows that the normal forces and torques are indeed the landscape gradient. Actually, the original measured forces and torques also match the landscape gradient reasonably well, but not as good as the normal ones. Now we will reconstruct the landscape using the measured roll and pitch torque. As I just showed, the experiment results prove that the contact torque are roughly the potential energy landscape gradients, but with sensory noise and friction. Due to this part, we cannot directly integrate the torque to get the landscape. Instead, we reconstructed the landscape using the Helmholtz decomposition. Helmholtz decomposition shows that any vector field can be separated into a gradient part and a circulation part. For the field of torques we measured, the gradient part is the potential energy landscape. Here we want to compare the reconstructed landscape from the measured data with that from the model. But first let me remind you what the landscape should look like. Here is the landscape from the simplest model evolves as the robot moves forward as the ground truth. And we only reconstruct a small part of this landscape in the region in the white box. Here we show the potential energy landscape we reconstructed from the Helmholtz decomposition and compare it with the ground truth. It shows that we can reproduce the shape of the landscape that matches the ground truth quite well. Although our study shows that the sensing contact forces and torques while sweeping the state space with controlled motion is sufficient to reconstruct the potential energy landscape, in real applications, a robot cannot systematically sweep the state space of the landscape as we did. Instead, it usually wants a single, zero-shot traversal with only under-accelerated motion. However, unlike a geometric landscape where we can leverage long-range vision to identify a least effort path in advance, on the potential energy landscape, the force sensing is roughly zero range, so the robot cannot know the overall shape of the landscape. It must move itself in the state space to reconstruct the landscape locally. Curiously, we found that when traversing beam obstacles, the cockroach actively oscillated its head up and down and rubbed against the beams. As active sensing behavior are observed in many species during exploration, like active touch from human, we hypothesize that the head oscillation is a similar active sensing behavior that will enable the robot to sweep the state space locally and reconstruct the local landscape that facilitates planning. As a preliminary exploration, we let the robot feed-forwardly oscillate its head while traversing the beams, and compare the torque measured from the result with that from a static head. Here we look into the roll and pitch torques. The dashed lines shows the landscape gradient as ground truth. The colored oscillated curves are the measured roll and pitch torques. If we filter out the head oscillation frequency, they are close to the landscape gradient. If we also add a measurement with a static head, We found that a head oscillation reduced the difference between the measured force and the landscape gradient. I would like to acknowledge my landmates who have helped and professors and friends for inspiring discussion and our funding sources. Thanks.